Good evening, everyone.
Good evening.
Good evening,
Good
sir.
evening. Good evening. So my slides are visible, right?
Yes, sir.
Okay. And my video is also visible.
Yes, sir.
Okay. So if you face any issue in between, please let me know. So let's wait for 3 to 4 minutes. After that, we will start.
Okay.
So is my pointer is also visible? My marker?
Yes.
Okay. Thank you. Is anybody new here? So for all of you, this is your second class, right? Or anybody is having this class as a first class?
Actually, I missed the first class.
Okay.
I have gone through the recording video. This is the first time online.
Okay. So Hitesh, so what is your motivation to join this course?
Actually, I'm working in the power plant, so I need to switch over through the renewable.
Okay.
That was the motivation.
Okay. Nice. Thank you. Anybody else?
I had attended a previous lecture which was conducted by Mr. Maiti, and also I have gone through your first video recording of your first. So I am a chemical engineer, and motivation to join this is I am basically inclined to work for a renewable energy. I'm a B certified energy auditor also, and since last 27 years I am working in a manufacturing chemical manufacturing industry especially. So
Nice.
my motive is now India is also going towards hydrogen energy. So and industries are also looking for new kind of things. So whether how we can switch from fossil fuels to this renewable energy as well as the hydrogen energy. So these are the areas of interest for energy people also. So that is the motivation to join this class.
Nice. Thank you. Anybody else? Okay. So I think we have waited enough. So now we can start. So once again, hello everyone. I welcome you all to the NPTEL live session number 2 for the course Hydrogen Energy, Production, Storage, Transportation and Safety. The course instructor is Professor Pratibha Sharma from IIT Bombay, and I am this course TA Amit Kumar Sharma. So as you all know, every Friday from 6 p.m. to 8 p.m. we have a live session. So the purpose of this session is to discuss the previous year's assignment questions and let you know how to solve the question, what are the patterns of the question, and also the course summary of the previous week. And if you have any doubt regarding the previous week, so we can discuss that here also. And the meeting recording, actually this meeting is being recorded, and the recording of this meeting will be shared to you from the NPTEL team. and this PPT will be also shared to you from the NPTEL team. So you can access the previous week's lecture and PPT also. So let's start. Okay. So this is the course outline. So if you face any issue regarding the slides, uh, regarding the pen and the video and audio, let me know.
Hey, hello. Hey, good evening. Can you hear me?
Yeah, I can hear you, Chandrasekhar. Yeah,
Uh,
please.
just sorry to bug you in between. The last sessions where we were not able to get the link, not the slides of the last sessions.
Okay,
Is
so
it?
I think some of you have already received the link, so maybe you have missed the link. So try to go through your emails. So there will be an email from the NPTEL team. There will be a link of Google Drive. So in that particular Excel file, you will get the Google Drive link for the PPTs and also the YouTube link for the videos. And if you
Okay.
have, and if you still not able to receive the email, then you can put an email to the NPTEL team that please share the link again.
Okay.
Or first, I
Thank you.
think I just advise you to go through your email once again.
Yeah. Okay.
Yeah.
No,
Okay.
let me share. It is available where all the course outlines are there, where the week 1, week 2 is there. Today only I saw even the PPT and the video also. So
Okay.
in the, at the end, it is written problem solving or something like that. So if you click that, you will go inside and there everything is there.
Okay. Okay. Right. Thank you then. Okay.
So
Thank
nice.
you.
Now you know where to find. Okay.
Yeah. Right. Thank you.
So the course outline. So in this course, we will cover hydrogen energy, basically the production. Sorry. Actually, let me set my pen. Okay. So we will cover the production, storage, transportation. So in the production, like from fossil fuel, renewables, storage, compressed storage, liquid, solid, transportation pipeline, vessels, tube trailers, and something about refueling stations, sensing and safety. So these are the areas which will be covered in this course. So today we will discuss about week 2. But first, in last week, uh, there was a query regarding the orthohydrogen and parahydrogen. Okay. So basically, the normal hydrogen mixture is having 75% of orthohydrogen and 25% of parahydrogen. So in orthohydrogen, the nucleus spin are parallel, and in parahydrogen, the nucleus spin is anti-parallel. So this is the main difference between the ortho and parahydrogen. And due to the parallel nuclear spin, they are having very high energy state as compared to the parahydrogen. So when you want to liquefy the hydrogen, then you need to convert this remaining orthohydrogen to parahydrogen. And also due to the different nucleus spin, they are having different magnetic properties. So the parahydrogen is used in the different magnetic techniques like in MRI and it is used in the MRI scans and also in the NMR spectroscopy. So these are the useful in these techniques, and also that they are having some other use. So to convert this to the ortho to the para, so you need to decrease the temperature, okay, and also you need a catalyst, so you can convert into the parahydrogen. So this is the difference. So basically the major difference is the spin of the nuclei, okay. So they are parallel in the ortho and anti-parallel in the para. And the parahydrogen is lower energy state and the ortho is higher energy state. So now let's start with the week 2. So in week 2, we have covered different types of reforming techniques. So you all know that reforming like is a method to convert a higher hydrocarbon methane into the syngas or basically hydrogen. So we have covered steam methane reforming, partial oxidation, and autothermal reforming. And we have also covered dry reforming, bi-reforming, tri-reforming. So let's see the major difference between these three first. The steam methane reforming, partial oxidation, and autothermal reforming. So the thermodynamics point of view, the steam methane reforming endothermic. So what is the meaning of endothermic? Anybody?
Heat will be required. Input heat will be required.
Yeah, input heat will be required. And what is the input heat required for the SMR?
It's a
The
combustion
fuel,
heat.
fuel. We burn fuel only.
And what is the
Combustion.
amount of heat required? Amount of heat.
206 kilojoules
Yeah,
per mole.
Yeah.
yeah.
20.
So 206 kilojoule per mole will be required for the steam methane reforming. The partial oxidation is exothermic process, so it will release heat, and autothermal reforming is a combination of steam reforming and the partial oxidation. So it is thermoneutral or slightly exothermic. So basically the heat that is required in the steam methane reforming, we can use the partial oxidation to use the released heat for the steam methane reforming. So it is the combination of both steam methane reforming and partial oxidation. So we can say it's thermoneutral or slightly exothermic. Heating required. So in SMR, external heat source required. We need to supply external heat source. We can use the flue gases and we can use a heat exchanger, or we can also burn the methane. Okay, and suppose if you are also having some other heat source, so you can use that to maintain the heat. In the partial oxidation, no direct heat exchangers. So we don't require a heat exchanger. There is no direct heat exchangers. The heat will be, it is exothermic process, so there is no heat requirement. In autothermal also, no direct heat exchanger because the partial oxidation will release heat and that heat will be used by the steam methane reforming reactions. Now, the thermal efficiency. Steam reforming is having very high efficiency. The partial oxidation have lower efficiency because the excess heat cannot be easily recovered. So because it is exothermic, so there will be excess heat. Heat is a lower grade energy and we cannot recover it, and it's difficult to recover. It will also increase the cost because to recover the heat you need to install some heat exchangers, and that will require cost. Degree of heat integration among various processes is lower than SMR, and degree of heat integration is also lower. In the ATR, higher system efficiency, then partial oxidation but lower than SMR. So it is in between. The heat generated by the partial oxidation reaction is fully utilized to drive the steam methane reforming reaction, but the excess heat is not easily recovered. So there will be some excess heat. So some heat will be used for the steam reforming and excess heat will be not recovered. Now the H2CO ratio. So it is the highest concentration of H2 3 to 5. It is 2 and it's 2 to 2.5. So this is actually a very important parameter because some process require a particular hydrogen to carbon monoxide ratio. So based on the requirement, they can select the SMR, partial oxidation, autothermal reforming. So sometimes the importance. So sometimes if efficiency is important, then they will go for steam methane reforming. But sometimes for a particular process, we require a particular hydrogen to carbon monoxide ratio. So if we don't have the exact ratio, then we need to maintain that ratio. And in maintaining that ratio, maybe we need to expend some more amount. So it's better to use a proper reforming method so that we can directly have the required hydrogen to CO ratio. So based on that, many industry players select the reforming method as per their requirement of hydrogen to CO ratio. Utilization of the syngas. So it is preferred when the rich H2 syngas required for application of pure H2 or pure H2 is required on large. Because you can see the H2 by CO ratio is 3 to 5. So there will be more hydrogen. So it will be used for if you require hydrogen rich syngas or if you want to use pure hydrogen. So you can use water gas shift reactor or PSA for the purification of the off gases. And the partial oxidation, it can be used where lower hydrogen to CO ratio is required, like methanol production or Fischer-Tropsch process. The ATR, a wide variation in the H2CO ratio possible by changing the oxygen to CH4 ratio or H2 to CH4 ratio. So in this method, we can vary this. Okay. How can we vary? So if we vary the oxygen to methane ratio or steam to methane ratio, so basically we change this ratio, and indirectly we are changing the available reactant for the reaction, so that automatically the product ratio will be changed. So in that way, we can change the ratio of H2 to CO by changing the ratio of O2 to CH4 and H2 to H2O to CH4. Thus, these ratios can be adjusted to get the desired syngas for the required application. Now about the reactor size and complexity. So in the SMR, reactor performance limited by the heat transfer, because reactors designed to promote heat exchange. Okay, so large and heavy, and are well suited for long periods of steady state operation. So you can see you will require large reactors. Okay, and also you will require large heat exchanging area also, because you are only, because it is endothermic, we are using external heat source, so we need to provide the heat to maintain it. The partial oxidation requires small reactor size because no external heating requirement. Okay, and the bulky heat exchanger, so we don't require bulky heat exchangers, we don't require external heating. However, several reactions occur, so system is complicated because there are some side reactions are also, so system will become complicated. In ATR, reactor size smaller than SMR but bigger than PX, so it is in between. No external heat source and no indirect heat exchangers. This makes autothermal reformer simpler and more compact than steam reformer, resulting in lower capital cost. Response time. So high endothermicity, since the reactor is extremely heated, as such startup and shutdown requires longer time. So startup and shutdown will require longer time. In the partial oxidation, short startup time due to fast exothermic reaction and fast response to load changes, safer operation desired. In the autothermal reforming, less NG natural gas required to support reaction is the startup and shutdown and faster response. So basically ATR is better in terms of response time. Requirement, superheated steam is required in steam methane reforming. Requirement of air or oxygen, if O2, then air separation unit is required. So if you require pure O2, then you need to separate out the nitrogen. Otherwise, because nitrogen inert gas, so your product will have nitrogen also. And maybe you don't require the nitrogen, so you need to install a air separation unit to separate out the nitrogen. In the ATR also, use of O2 requires air separation unit and superheated steam. So it is the combination of both. So you require both superheated steam and the air separation unit. Now in terms of heat transfer related, so heat and mass transfer related limitation as well as chemical kinetics related. So there are some limitation due to chemical kinetics and due to the heat and mass transfer. In the past oxidation also, hot spots and no uniform temperature can lead to possible sintering and need to be operated below the explosive limit. So it is exothermic, so there will be some hot spots also. In the ATR also, use of steam controls the temperature. Beside the endothermic reforming reaction, after the exothermic combustion controls the overall temperature. So regarding the overall system, so the SMR is heavy and large system. Partial oxidation is compact but complicated. ATR is simple and compact. Catalyst challenges. So in steam methane reforming, carbon deposition due to some reaction, so there can be Bordeaux reaction, methane cracking. So however, the reaction temperature lower, so decomposition reaction less favorable, and sintering is lower compared to the partial oxidation and ATR. So the sintering is lower compared to these two methods. In the partial oxidation, no catalyst deactivation problem is non-catalytic process. However, catalyst deactivation and sintering in catalytic process due to both the carbon deposition and high temperatures. Non-uniform heat and mass flow can lead to further sintering, breakage, and catalyst consumption is high. And in ATR also, intermediate temperature, both deactivation and sintering can be there. However, due to presence of steam and deactivation and sintering is lower compared to partial oxidation. So operating condition important. So it is operated between the 700 to 900 degrees centigrade and 50 to 30 bar. Lowest temperature requirement. The pulse oxidation, the temperature is 1000 to 1400 degrees centigrade and the pressure 30 to 80 bar. And ATR also 800 to 1300 degrees centigrade and 20 to 80 bar. Thermal management. So as we can see, the operating condition, the temperature is not that much high, so the management will be easy as compared to these two processes. So thermal management and thermal integration very essential. Besides, steam can corrode and special materials required for reformer tubes to sustain the reaction condition. Because we are using steam, so much of steam, so you need to also look into the corrosion part. The partial oxidation require refractory brick lined surface due to metallurgical constraints. So because the temperature is very high, so it will be difficult. So use of a metal reactor will be difficult due to metallurgical constraints. So it's better to use brick line furnace, refractory brick line furnace. Less thermal integration and management required compared to SMR. Better thermal management than partial oxidation and less of insulation related requirement because the generated heat will be used for the SMR reaction. Fuel consumption. So the fuel consumption, response time and system required for startup is complicated and higher. So it required higher fuel and also the response time is higher. Least amount of fuel required to provide the appropriate reaction condition. So the least amount of fuel required in the partial oxidation. Less of fuel consumption to support reaction. Efficiency the highest in SMR, lowest in the partial oxidation and higher than partial oxidation but lower than the SMR. So it is in between. So these are the advantage and limitation regarding the steam methane reforming, partial oxidation and protothermal reforming. And we also covered bi-reforming, tri-reforming. So we will look those into our further slides. Yeah, Selva Kumar.
So this dry reforming, how best the process comparing SMR and POX and
So
ATR?
dry reforming, we will come to dry reforming later actually during the question. So at that time we will discuss that. So now we have
Okay.
covered steam methane reforming, partial oxidation and autothermal reforming. So
Okay.
the remaining reforming will be covered in between the questions. Okay,
Okay,
so
right. Thank you.
yeah, so let's start with the questions. I hope you all have gone through the professor's videos because if you're not gone through this time, so I request you all before the next class, I advise you to go through the professor's video so that it will be easy for you to understand the questions and also you will participate in the question. So if you participate, then it will be a very good thing. So we can discuss more. So the question number 1 is sweep gas is used in space process. Steam methane reforming, option A, B, sorption enhanced reforming, C, hydrogen membrane based reforming, and autothermal reforming.
C, hydrogen membrane.
Okay, let's wait for 1 minute. Think about it and let me know the answer. We have one answer. C,
Yeah,
hydrogen
it is
membrane
C.
based reforming.
It is C
Yes,
only.
the hydrogen membrane.
Okay. So the SMR, what is the basic of SMR? Anyone? Like this basic element of steam methane reforming. Like
Required a
we,
feedstock and a heat.
so yeah, we require a reactor, simple reactor, feedstock. We have to maintain the temperature. We require steam. So these are the main requirement for steam methane reforming. Okay, what about the sorption enhanced reforming?
We need some
Catalyst is
to absorb I mean, some of the products. We need to remove some of the products. So deabsorption kind of things.
Yeah. So basically sorption, so we need to sorb the CO2. So we need a catalyst that can, so the CO2 can be sorbed on that particular catalyst and we can separate out that from the reactor itself. So we don't require further processing of the off gas. What about the ATR? So as we discussed earlier, ATR is a combination of steam methane reforming and partial oxidation. So we require steam, oxygen, reactor, catalyst, and the feedstock. So these are the basic things. Now come to the hydrogen membrane based reforming. So what is this?
It is just opposite to the sorption. Here we take out hydrogen only through this membrane. So that membrane is selected in such a fashion that it only allows hydrogen to pass through. And
Yeah.
just to maintain pressure difference, we use sometimes sweep gas.
Yeah, this is important. So to maintain the pressure difference, and what is the meaning of pressure difference to, so do you want to explain it more?
No, you want me to explain something more?
Yeah, like you
Uh,
told now the pressure difference. So where
yeah,
we use the pressure difference in membrane based reforming.
yeah. I was going through that video lecture, and if you
Okay,
see
okay,
the
okay.
construction, then there is a two drum kind of things.
Yeah, okay.
So all reactants are input in the outer drum, and then hydrogen passes through that inner one. So there has, both the drums, there has to be some pressure difference. Then only that membrane will act.
Yeah,
This
right,
is
right.
how roughly I have understood.
Yeah, nice, nice. So like Manoj has already gone through the video, so it will be good if everyone will go through the videos. So the correct answer is C. Okay, the hydrogen membrane based reforming. So the sweep gas is used in hydrogen membrane based reforming process to maintain the pressure difference and to for the partial pressure to create partial pressure and to for so the hydrogen can be separated. So this is the diagram you can see. So this is inner tube. So you can see the membrane. This is the membrane. You can consider the membrane. This tube is a membrane. Okay. So it's having a particular material. So here you can see the feed and the feed outlet. There is a catalyst. Okay. And there's a permeate. So this is the membrane. So you can use packed bed, fluidized bed, or micromembrane reactors. Okay. So this is a packed bed membrane reactor. So when you supply the feed, so it will have a particular pressure. So membrane will act like, so it will only pass the hydrogen atom. So hydrogen atoms will pass through the membrane and come inside. Okay. And then we need sometimes sweep gases so that we can maintain the required partial pressure inside the pressure difference so that the hydrogen molecules from this area will diffuse into the membrane. To maintain that, we need sweep gases. Okay. The correct answer is C. So the hydrogen membrane reactor, you can see the basic reaction of CH4 and H2O. It is reaction of steam methane reforming. So it converts into the CO, the H2. So the removal of H2 to favor forward reaction. So because we know that whenever we are having reforming, so there are also some side reaction. Okay. So if we don't favor if we want to favor the forward reaction, then we have to remove the hydrogen. So if we continuously remove the hydrogen, so there will be less product available for the reaction. So that will not take part in the side reaction. Okay. So only the forward reaction will be favored. And also the conversion of CH4 same as the conventional SMR, but at milder condition. So in the hydrogen membrane reactor, the conversion of CH4 is similar to the steam methane reforming, but at milder condition. You don't require that much temperature and all. Higher conversion, but at same operating condition as that of the conventional SMR. Also the membranes regarding the membrane, so it should be high selectivity of H2, okay, as against other products. So whenever you select the membrane, so it should have high selectivity of hydrogen. It should be thermal and mechanically stable. Okay. So these are also the conditions regarding membrane. It should be also economical. So basically the transport mechanism of hydrogen inside a palladium membrane. So suppose if you are having a palladium membrane, so it follows a solution diffusion mechanism. So hydrogen molecule is adsorbed onto the surface of the membrane. Then it is split into hydrogen atoms. Okay. Then these atoms go across the membrane through diffusion and then recombine again into hydrogen molecule on the low pressure side of the membrane. Then it is dissolved from the surface. So this is the phenomena. By the way, this is palladium membrane. Okay, Selva Kumar, you want to say something?
Yeah, yes. What is the term selectivity, hydrogen selectivity?
Okay. So selectivity, once a minute. Okay. So you can see there is a reaction. So suppose if we have a reaction like A plus B and C plus D. So we want to form like our main product is our target is D. Okay. So we want more D. So we want to have, and also maybe the reverse of reaction is also possible. So it depends on the equilibrium of the reaction. Okay. So to have more D, so then as compared to A and B. Okay. So basically you want the main forward reaction. So you will maintain the condition like that. So your reaction will be forward favorable. So that you will have more amount of D. So that's selectivity. So if you want to like more C, so you will maintain the conditions because there are also side reaction. So you will maintain the conditions to have more amount of C. So that will be selectivity of C and selectivity of like D. So we want to see the hydrogen selectivity. So the condition will be like that. So there will be more hydrogen. And I'm just forgetting the exact formula. There is also a way to express selectivity. Anyone remember? It's the ratio of the product to the reactant, I think. The desired product to the undesired reactant. Am I correct?
Yeah, correct. Actually, in the last week, in the calculation discussion, I saw this term. In
Yeah.
the particular sum, there was a question for calculation of hydrogen selectivity. So that's why I raised this question.
Yeah. Okay. Okay. So the next question is the pressure required in non-catalytic partial oxidation process is. So what is the pressure required in non-catalytic partial oxidation process?
Sir, I think it's a 50 to 80.
Okay, so these kind of question you can only answer if you have gone through the videos. So because these are direct questions. So anybody else?
Yes, 50 to 80 bar, correct.
Okay. So let's say what is non-catalytic partial oxidation?
Catalysts are
Partial
not used
oxidation
in the
without
partial
catalyst.
oxidation.
Okay, so partial oxidation without catalyst. Okay. And okay, because the name itself is saying non-catalytic, so it means that there will be no catalyst. But and what are the applications of this process? Where we use this process?
Where transportation is not required that much.
Sorry, where?
Where transportation of hydrogen is not required, it is in heat process.
The transportation, I think transportation is not a reason, a good reason to use a non-catalytic process. Sometimes you can use the steam methane reforming also, and you are using the hydrogen in your industry only. You are not transporting it. but still you are using the steam methane reforming. You are not using the non-catalytic partial oxidation.
To avoid the deposition of the sulfur, so that we can prefer non-catalytic box.
No, because you can see it require very high pressure. So, and catalyst is not there, then you see the temperature will be very high. Because if you are having a catalyst, then that can lower the activation energy for the reactions to occur. But if you are having non-catalytic, then you need higher pressure and temperature. So only for this reason, it's not advisable. So basically, what do you think about the feedstock? Think in the direction of feedstock.
We can use many I mean of fuels. Fuels is we can use in number of fuels which is coming from hydrocarbon industries.
Yes, yes.
Olefins and
Yeah, right. So due to the fuel availability, like in a refinery, so we are refining crude oil to many products. Okay. So, but still in each process, there will be some kind of hydrocarbon will be left out. Okay. So by non-catalytic partial oxidation, we can reform number of hydrocarbons. They are very difficult. If we use like normal reforming method, then they will deposit so much carbon and they are very difficult to reform. Okay. So the non-catalytic partial oxidation process will occur at high temperature, pressure. So we can do the reforming for those. So let's see about it. So it is the correct answer is A, 52 80 bar. So these are the conditions. So in the absence of catalyst, the temperature is higher. Okay. You can use gaseous, liquid or solid hydrocarbons. There will be no catalyst poisoning challenges. You can use air or oxygen. Pressure you need to maintain 50 to 80 bar. The temperature you can see 1200 to 1500 degrees centigrade. It's very high temperature. The hydrogen to CO ratio depends on the feedstock composition and the quality of the steam added. So it will depend on the feedstock composition and the quantity. So basically the quantity of steam. So basically we are varying the ratio of steam to carbon. So there are two commercial processes available in the market. Exco gas generation process, TSGP and shale gasification process. So you can read more about these two processes. And difference between the two is gas cooling process, waste heat recovery unit, design of nozzle and removal of soot. I think one of you is unmuted. Please mute yourself. Edwin? Okay. Okay. So the major difference is in these two is the difference between the cooling process, waste heat recovery unit, okay? Not in the main core process, but only the side process. Grading bottom of barrel low value fuels, so we can use the bottom of barrel. So and low value fuels can be used for acetyl fuel and methanol synthesis. And these are the reactions involved in the non-catalytic partial oxidation. So you can see a hydrocarbon with N/2 oxygen is exothermic reaction. Then also if suppose your hydrocarbon is also having higher sulfur compound, then also exothermic. Then like endothermic, like type of a steam reforming. Okay, it's kind of endothermic. It's kind of a dry reforming. It's also endothermic. Then exothermic, like kind of a gasification. It's also endothermic. It's a water gas shift reaction. So these are the reaction involved in the non-catalytic partial oxidation. So you can, by changing these quantity of steam and all these the operating condition, we can change the amount of H2 to CO. So basically we are changing the reaction rates and all these things. So this is a schematic of non-catalytic partial oxidation. So you can see you're supplying air, then you need a ASU. You need to separate out the nitrogen, otherwise your nitrogen will be in your pure with hydrogen. So your hydrogen will be not pure. Okay, there will be some part of nitrogen also. So you need a ASU. Then you can see here is a reactor. Okay, so its operating temperature 13 to 15 degrees centigrade. You're supplying O2 and you're supplying heavy oils. So see, the feedstock is not natural gas. The feedstock is heavy oils. Okay. Then you are maintaining the temperature and pressure. There will be some carbon shoot. Okay, that can become out. Waste water will be there. So syngas will go to the water gas shift reaction. But we know shift reaction occurs at lower temperature. So you need to have a cooler. So this will act as a heat exchanger, and it will also, so you can see that the outer temperature will be near maybe 1300 to 1500 degrees centigrade, but here the temperature will be 340 degrees centigrade. So we need to reduce this temperature. So we use a heat exchanger and also supply some water into that heat exchanger and generate steam by using the heat of this stream. And we generate steam, and steam can be supplied into the. One of you is unmuted. Please mute yourself. Ravi Krishnami. Okay, I request you all, please check your mics. Okay, so only unmute yourself when you want to ask something or you want to say something. Otherwise, please be muted. Am I audible? Because there is a question, is there sound or not? Is my voice is okay?
Yeah, clearly audible.
Okay, okay, thank you. So I think Gautam, please check your speaker. Maybe there is some issue with your speaker. Okay, so you can use a heat exchanger. So because we need steam. So we need steam in the water gas shift reactor and also in the this reactor. So we can use this heat to generate steam, and we can supply steam to both sides. Then you can use the acid gas cleaning. Okay, and you can have the pure hydrogen, and you can also remove the sulfur. Okay. So this is the like steam added to reduce formation of carbon, act as a moderator to reduce temperature and hotspot. So because it's a very high temperature, maybe some part will have low temperature, so there will be temperature gradients and it can create hotspots. So steam will act as a moderator to maintain this, also promote water gas shift reactor, act as a quenching and washing medium. Feedstock can be natural gas, petroleum residue, heavy oils, petcoke and coal. So you can see the variety of feedstock. So we can use uh, different kinds of like heavy to lighter hydrocarbons in this heavy oils, and we can reform into hydrogen. So the known further about this is, you can see this is like the design of reactor. So there is a flame region, okay, and the heat exchanging region. So there are two regions, flame region and remaining heat exchange region. And the reactor is type of a brick lined reactor, okay, because you can see the temperature is very high, so you cannot use a metal reactor. So brick lined reactor is preferred. There is no indirect heat exchange, so you can see that there will be burning of fuel, and directly that heat will be used for the remaining reactions. So there is a direct heat exchange, no indirect heat exchange. Heat recovery is poor. Heat losses are very high. Heat losses are there. High conversion can be achieved. We can achieve very high conversion. More compact, simple and less costly reactor efficiency, you can say 60 to 75%, less hydrogen. So energy efficiency is 15.9 to 19.3 megajoule per normal meter cube. Important in refineries. So it's very important in refineries because in refineries they have different kinds of residual hydrocarbons, so they can use those because they cannot directly dump those hydrocarbons, so they can use in non-catalytic partial oxidation process to further convert them to hydrogen. So next question is autothermal reforming is A, highly endothermic, highly exothermic, thermoneutral, slightly exothermic or exorgic.
It, it's a C.
Thermoneutral.
Thermoneutral, slightly exothermic.
Yes, see.
Okay, C. So I think we have already covered. So what about the autothermal reforming? What is a, so it is combination of which reformings?
SMR and partial oxidation.
Okay, SMR and partial oxidation. So the heat required for the SMR will be supplied from the partial oxidation reaction. The correct answer is C. So this is about the autothermal reforming. So this reforming have both the advantage of steam methane reforming and partial oxidation. Okay, you can maintain the H2 to CO ratio and also thermoneutral process. So the oxidant here we use O2 or air. If you are using air, then there will be some nitrogen, and as per your requirement, suppose if you are using that in the fertilizer industry and you want to form ammonia, so you can use air as an oxidant, and if you want pure hydrogen, then you can use oxygen as an oxidant. And we already covered you need a air separation unit to have pure oxygen and the combination of steam. So there are two oxidants available, O2 and steam. Advantage is thermoneutral process and slightly exothermic. Higher H2 and CO ratio than partial oxidation. Heat required supplied internally. So we are not supplying the heat from external means. The heat is supplied through internally using the partial oxidation exothermic reaction. The product gas composition, so it's a thermodynamic equilibrium at temperature and pressure. The composition and flows of the feed, the ratio of oxygen and steam added in the reactor. So the composition will depend on these things. Equilibrium temperature and pressure, the flows and the feed. Okay, the steam amount of the steam to carbon ratio, steam to carbon to O2 ratio. Okay, so the ratio also depend, the product gas will be depending on these things. So this is a autothermal reactor. Okay, so basically you can see there are three zones: combustion zone, thermal zone and catalytic zone. And you can see the supply of oxygen is here, then the natural gas and steam, and here is a burner also. So burner is the key component of autothermal reforming. So it maintains uniform temperature, it reduces soot formation and proper mixing of reactant and oxidant. So in the combustion, the fuel, some part of fuel will react with the oxygen and combustion will happen. It will release heat. So in the thermal zone there will be so much heat. So here the reaction will happen, water gas shift reaction, steam methane reforming, and hydrocarbons will react. So in the combustion zone, these are the reaction involved. In the catalytic zone, you will use a catalyst, and the steam methane reforming and water gas shift reaction will happen. So these are the reactions. Okay. So these are exothermic reaction. It's endothermic. So it will get the heat from the thermal zone or from the combustion zone, thermal zone. The front of the catalyst bed experience high temperature. So the front of this catalyst bed will experience very high temperature as compared to the lower side. So there will be also a thermal gradient. The CO content higher than SMR, H2 CO ratio lower, and high shift activity required. The water gas less favorable in reformer and faster kinetics. Reactions are fast, startup can be fast. So the kinetics are very faster. Okay, so because the temperature is very high, temperature is high, okay, you're having a catalyst and you don't need the external heat, faster kinetics, so startup can be faster. Autothermal reformer is a refractory brick line reactor with three regions or zone: combustion zone, thermal and catalytic zone. So here you can see we are having pure O2. The natural gas, if it is having any sulfur, then we are having a desulfurization unit. So it can remove the sulfur. Then we are having adding a steam and using a preheater to maintain the temperature. We are supplying it. Then reactions are happening. Then syngas. Then we are doing cooling. Then having water gas shift reactor. Then we can do purification. So we can separate out the hydrogen against the CO2, and also the remaining tail of gas can be used in the steam generation. So we can have a, like in this preheater, like we can use some kind of a combustion in between and use the heat in this preheater to preheat the natural gas and steam. So by adjusting the oxygen to methane and steam to methane ratio, we can so the process can be thermoneutral or slightly isothermic. It can determine product gas composition, temperature and pressure, conversion selectivity. Typical H2O to carbon and O by C ratio in the ATR are around 1 to 2 and 0.5 to 1 respectively. So these are the typical ratio for the ATR. Okay, so I forget to use animation for the answer. So the question is, hydrogen to carbon monoxide ratio in dry reforming under ideal condition is. So you can see the answer is 1. Okay. So what is the reaction of dry reforming? You can see CH4 plus CO2, 2CO plus 2H2. So it also considered like stoichiometric reforming. So H2 by CO ratio is equals to 1. The heat required for these reactions is this reaction is 247 kilojoule per mole. Okay, and what was the heat required for the steam reforming in previous slides? What is the heat requirement
06.
for the steam? So so the steam reforming required 206 kilojoule per mole,
206.
and dry reforming required 247 kilojoule per mole. Okay, so this reaction is more endothermic. The advantage of dry reforming is that both methane and CO2 are greenhouse gases and we are using them. Okay, so basically we are reducing the greenhouse gas emissions. If natural gas have both in high concentration, then dry reforming. One is highly reduced form and one is highly oxidized form of carbon. Can be used for process where carbon monoxide is gas required and H2CO ratio equals to 1. So suppose if you require H2 by CO ratio of 1, then the dry reforming is preferred reaction. So it can be also used for the production of acetic acid, synthesis of dimethyl ether, direct conversion of syngas into olefins through the Fischer-Tropsch process to the olefins reaction, FTTO. It's highly endothermic process because you can see it required 247 kilojoule per mole of heat. So the possible reactions in dry reforming. So the first reaction is the CO2 plus H2, CO plus H2O. So what is this reaction? Anyone? We have seen this reaction already.
Sir, it is a reverse of water gas shift reaction.
Yes, nice, nice. So it's a reverse of water gas shift reaction. Okay. So you can see the forward reaction is normally CO plus H2O. The CO react with the steam to generate hydrogen and carbon monoxide. So we use a water gas shift reactor after the reforming reactor to convert the remaining CO into hydrogen. But sometime if your temperature is in the like a little bit high, and also like the conditions are favorable for the reverse water gas shift reaction, then this reaction will occur. So your CO2 and H2 will react and form carbon monoxide and steam, and it's endothermic. Okay, and the water gas shift reaction is exothermic. So that is favored at lower temperature. It is favored at higher temperature. Second reaction is CO2 plus 4H2, CH4 plus 2H2. So you can say the methanation reaction. So basically we are forming the methane. Again the CO plus 3H2, CH4 plus H2. What is this reaction? So it is
This
also
is
the
reverse
reverse of
SMR.
Steam
reverse
methane.
SMR. Yeah. So basically it's called methanation reaction. So this can also occur. So these are the possibility of reactions. So the temperature range is 900 to 1200 degrees centigrade. H2 ratio can be controlled and can range between 0.7 to 1.9. So by changing the CO2 to CH4 ratio, you can change the H2 to CO ratio. It is dry process because then as the name suggests, dry reforming. So we are not using steam. Okay. So basically steam methane reforming, we are using steam. But it is dry reforming. So we are not using steam, but still we are reforming the methane. So that's why it's called dry, but you can add steam also. So if you add steam, then that will reduce the carbon formation. So because you will have more oxidant and steam, steam will avoid the formation of carbon. Also, it is due to the carbon deposition, there will be catalyst deactivation. And if the catalyst deactivation is there, then in after some time, your reactor will fail. Okay. So there are 4 reactions responsible for catalyst deactivations. The first is bordered reaction. So you can see the 2CO, CO2 plus C. So the carbon monoxide dissociate in the carbon dioxide and carbon. So this carbon will deposit on the catalyst surface, and it can detach the catalyst from the support. It can decrease the active area of the catalyst. So in multiple way. So it will finally deactivate the catalyst. So it is exothermic reaction and favorable at lower temperature. Then reduction of CO. So the carbon monoxide plus hydrogen is H2O plus C. So it is exothermic reaction, but although occurs at lower temperature but with higher Gibbs energy. So it's not referred route except case when there is high partial pressure of H2. Methane decomposition. So CH4 carbon plus 2H2. It is also favored at high temperature, endothermic reaction. Reduction of CO2. So CO2 plus 2H2, carbon plus 2H2. So exothermic. So reverse of any of these reaction can result in removal of coke formed. So if these reactions are occurring in forward direction, they will deposit the coke, and if they are occurring in reverse direction, then they will remove the coke. Okay. So if you are having like excess steam, then you can basically remove the coke. That's why steam is advisable to add in the reforming. So gasification of coke, the nature of support, desirable is the basicity of the support, and also lower at higher temperature and higher CO2 CH4 ratio. Okay, so as we have discussed about dry reforming, so which type of carbon? Because we know that carbon deposition is a very critical phenomena for dry reforming. It can deactivate the catalyst. So which type of carbon formation for carbon is not formed in dry reforming process of methane? So there will be different kind of carbon formation will be there. So the question is, which type of carbon is not formed? Whisker,
Option D.
pyrolytic, gum, or lonsdaleite?
Option D. Launched that.
Option
It's a
D.
launch daylight.
Okay, so we have option D. Anybody else think about it? Okay. The correct answer is option D. So it means that there will be formation of whisker carbon, pyrolytic, and gum carbon. So let's see about these. So because if we are using CO2 as an oxidant in the reaction, in the reforming, then we have already covered the reactions involved in the carbon deposition. So there will be higher possibility of carbon formation. Okay. So three types of carbon will be formed: whisker, pyrolytic, and gum carbon. So whisker and coke at higher temperature, while gum at lower temperature. And the pyrolytic carbon in case of higher hydrocarbon. So if you are using higher hydrocarbon, then there will be pyrolytic carbon and normal methane and like that. So whisker carbon will be there, and the gum will be at lower temperature. Gum covers at catalyst by layers of graphene type carbon. More problematic is whisker formed at high temperature, low steam to carbon ratio, and presence of aromatics. So it is more problematic because it will try to detach the catalyst from the support. So small size of catalyst and high dispersion desirable and appropriate operating condition. So to reduce the catalyst deactivation, it requires the small size of catalyst and high dispersion desirable and appropriate operating condition. The next question is, direct heated type receiver has space as compared to the indirect heat type receiver. High temperature, low efficiency, poor heat transfer, and low temperature. So it is like, if we are considering the heat type receiver, anybody want to say something? So from which topic this question is?
This alternate energy for
Yes.
the heat source.
Sorry?
Alternate energy or heat source for the
Yeah.
reforming. Yeah.
Yeah, right. So what is the heat source in this question?
It will be high temperature.
Is it
Yeah, Mukesh?
is it a sunlight?
Yes.
Solar?
Solar, yeah, right. Anybody else? Okay, so this question is from the topic of, like, if we are using the solar energy for the reforming. So now the question is, direct heated type receiver has space as compared to the indirect heat type receiver. So option A, high temperature, lower efficiency, poor heat transfer, or low temperature.
Option A, high temperature.
Okay.
Option A.
Anybody want to
I
explain
think
this?
it's D, low temperature.
Okay, now we have conflict. A, high temperature, D, low temperature. So
High
first,
temperature.
those who are with high temperature, if anybody wants to explain, please explain.
So this direct receiver, direct heated receiver, there is no loss due to conduction due to some other external medium. So there is no loss in energy.
Right. Anybody else? Okay. So let's see. The correct answer is A. Yes. So yeah, in direct heater type receiver, it will receive energy directly. It's a one point, and we will cover if there is any other point also. Let's see about these things. So solar assisted methane reforming. So as of now, we have covered different reforming techniques. So in those techniques, we are using either we are like using the combustion heat from the combustion of oxygen and fuel. Okay, either we are using some external means of heating. Okay, and either we are using the combination of both. So, but in this, we are using the solar radiation. So it is solar assisted methane reforming. So the concentrated solar radiation. So we use the concentrated solar radiation in a way that, because if you know the radiation are not concentrated, because if we go into sunlight, so we are feeling little warm. Okay, if you are like in the winter, then you will feel good. So we don't think that this temperature can go up to our required temperature of reforming, that is near 800, 900 degrees centigrade. So how can we achieve that temperature using solar radiation? So we need to concentrate that. Okay. Anybody, do you know the number? What is the solar radiation per meter square? Energy per meter square? Solar energy per meter square? So the solar constant. So it is nearly around 1300.
1367, I think.
Yeah. So 1367 is the exact. So 1367 watt per meter square. Okay. So and roughly we can get around 1000 watt per meter square, because due to the clouds and different kinds of other phenomena. So the actual receiving on the surface will be around 1000 watts per meter square. So if we use some type of concentration, some type of equipment that can concentrate this energy at a particular point, then we can achieve the required heat to maintain the temperature of reforming reactor. So we have 4 technologies to achieve this: the parabolic trough collectors, linear Fresnel reflectors, parabolic dish, and the tower with central receiver. So these are the 4 technologies available. The parabolic trough and linear Fresnel moderate solar concentration ratio and achieving temperature less than 500 degrees centigrade. So these two can achieve temperature less than 500 degrees centigrade. Okay. The parabolic dish and central tower receiver preferred. So these are preferred because they can have the temperature required for the reforming. So we can operate either a open loop or closed loop type of system. So in the open loop system, the syngas produced, so we are having a reforming, so syngas will be there. So in the open loop, we use that syngas in the gas turbine combined cycle plants to have to generate more power. So it will be more efficient. In the closed loop system, we will store the syngas, transport it. We can do the methanation. We can like convert the syngas into methane, and again we can use the reforming and used for the process, heat or power generation. Provides long-term storage, thermal energy transport, can be integrated steam power plant or used for high-grade process heat. And for solar receiver, we can use directly or indirectly heated based on the solar heat transfer to the HTF. So now let's see the indirectly heated receiver. So in the indirectly heated, you can see the sun is coming to a part and it is reflecting the sun rays to the reactor. So we have 3 kinds of reactor. In this, we have a wall, then there is the product gas inside, so it is heating it. Here we are having a like kind of a heat exchanger, you can say. It is allothermal, and here we have a kind of catalyst bed. So you can use like mediums for the heating like air, molten metal or molten salts. So heat transfer to the working fluid does not take place upon the surface which is exposed to the incoming solar radiation. So this surface is exposed to the radiation, but the heat transfer is happening here actually. It's an indirect one. In the directly heated receiver, so there will be stationary absorber and volumetric receiver family. And also they are like kind of having absorbing matrix absorb and transfer to the working gas. So there will be some kind of matrix they will absorb and transfer to the working gas or like our methane. It can sustain thermal stresses. Radiation absorbed by the materials and transfer to the gaseous heat transfer medium. Okay, so some like honeycomb type of structure or some different kind of structure will be there. They will absorb the energy and transfer to the gaseous uh, molecules, and it can achieve high heat flux, high temperature, and higher efficiency. Absorber can be steel or ceramic wire meshes, ceramic foams, multi-channel honeycomb. So the absorber that is used for the heat receiver as a heat receiver can be steel or ceramic wire meshes, ceramic foams, multi-channel honeycombs. So next question is, what is the conversion percentage of methane using plasma? So you can see the answer is 98%. I again forget to use the animation. Sorry. So what about this plasma reforming? So first is, what is the plasma? So you can all see the plasma is a fourth state of matter. And what are the remaining three states? So it is the fourth state of matter. The remaining three states are solid, liquid, and gas. So it consists of electrons, ions, radicals, neutral molecules, and ions. It's created by applying electric field. Discharge created in this way that in the way will depend upon the gas characteristics, electrode arrangement, and on the applied voltage. So these are the things that we can. So the plasma will depend on these things like electrode arrangement, applied voltage, and the gas characteristics. The plasma produces not only the ideal temperature required for the reaction, but also free radicals and ions can be used for SMR, partial oxidation to thermal reforming. So it will also require, it will also give the heat required for the reaction, but also free radicals and ion for the to support these reactions. Equilibrium, hot or thermal, and non-equilibrium plasma, cold or non-thermal. So two kinds of plasma will be there, equilibrium, non-equilibrium. Let's see more about this. So the correct answer is 98%. So the conversion percentage of methane using plasma is 98%. So now the thermal or non-thermal plasma. So thermal plasma created at higher pressure, and by applying, so it is created at higher pressure, applying either DC, AC or RF source, and have temperature around 2000 to 20,000 Kelvin with high energy density created by arc or plasma torch and inductively coupled RF discharge. On the other side, non-thermal plasma created at low pressure and temperature. So this is a major difference. So the thermal plasma is at higher temperature, higher pressure, and applying the DC, AC or RF, and the non-thermal plasma at low pressure and temperature. The temperature of electrons and heavy particles different, use lower power. It requires low energy density, like low discharge, gliding arc, dielectric barrier, and corona discharge. Okay, the pulse discharge, etc. Catalyst can be used in this method to reduce the required activation energy for hydrogen production. The temperature involved are 600 to 1000 Kelvin. So the difference is huge. Okay, so this is the difference between the thermal and non-thermal plasma. Now
Amit,
the non
Amit, sorry to interrupt. I have a meeting,
yeah.
so I have to leave.
Yeah, okay, sure, no issue.
Thank you.
No issue. Yeah. Now the non-thermal plasma reforming is it occurs at low pressure, low temperature catalyst used which can change the pathway of reaction as active species gets absorbed on the catalyst surface. It can change discharge characteristics, ionization and dissociation characteristics, chemical reactions by the high energy electrons. Okay. For the high electron energies, then formation of C2H2 by removing hydrogen, while if lower energy is involved, then less hydrogen being removed from the CH4 resulting in C2H6. So these are the things you can go through. You can use a reference book to learn more about this plasma reforming. And in the thermal plasma reforming, high temperature leading to carbon hydrogen bond breaking to form solid carbon and hydrogen. So because there is a high temperature, then the carbon hydrogen bond will be there. So you can say the methane cracking can happen. So that will break the bond and solid carbon will be deposited on the catalyst. Suppose if it is using the catalyst or not. Let's see. So the offers higher capacity, high energy conversion efficiency, high energy density and chemical active species which can result in better conversion. Conversion is higher as 98% using DC arc plasma. The plasmatron or thermal plasma operated at very high power densities can result into the required reaction with formation of intermediates like active species and free radicals. It's fuel flexibility. So you can see it's operating at very high temperature. So any fuel can be reformed. So fuel flexibility is there, better control or process and getting desired gas composition can be achieved. Various demonstrations with different plasmatrons have shown 40 to 50% hydrogen in the product gas composition and specific energy consumption around 40 megajoule per kg H2. So the specific energy consumption is around 40 megajoule per kg of hydrogen. It is highly endothermic process. Better conversion can be achieved with thermal plasma either with RF or microwave power. So in summary, we can say the various plasmatron demonstrated and the parameters, okay, and the advantage. So the fast reaction rate, small and compact, fuel flexibility, good control of the process, good control over the product gas composition, okay, tolerance to poisoning and carbon deposition. Disadvantage is the hydrogen delivered at lower pressure and dependence on the electric energy. So because we know that due to the density, lower density of hydrogen. What is the density of hydrogen? Anybody?
0.08.
0108.
0.08. Density.
Yeah, 0.08. Without unit, what is the unit of density?
kg per meter
It's a
cube.
kg per meter cube. Yeah.
Okay. Is it okay,
No,
or do you want to?
no, it is at normal temperature,
Yeah,
normal
yeah,
ambient condition.
yeah. So it's very important. So whenever, like, just remember it. Whenever you are like reporting density, and the pressure and temperature is also very important because for a gas, the density can change with pressure and temperature. Okay, so you need to also mention the condition operating the conditions. So you see the density is very low. So to use the hydrogen, we need to compress it. So because the delivered hydrogen lower pressure, so we need to spend so much energy in the multi-stage compression to compress the hydrogen up to maybe 600 bar or 800 bar. Okay, as per the requirement. So what is the temperature of flame in burner region in the ATR process? So in the ATR process, we have covered, there are how many regions? So we have covered three zones or three regions. Yeah. So one of the region is the combustion, 10.
Combustion.
C 1200 to 1300.
So let me know the three regions. First is the in where the combustion happens. Then what? Then what?
I think the thermal zone,
Thermal
and
zone, yeah, and the catalytic zone.
yeah.
Nice. So now let me know the temperature of flame in the burner region. So where this burner region will be?
At the neck of the reactor.
Yeah, yeah. So it will be in the combustion zone. Okay. So what will be the temperature of this burner region? Option A 1000 to 1100, B greater than 2000, C 1200 to 1300, D 1400 to 1500 degrees centigrade.
It is C.
It's 1220 to
1200 to 1300.
1300.
Okay, we have one option C, and I think one of you was saying some other option. Anybody?
Since the reaction temperature is very high, the flame temperature, I guess it should be greater than 2000 Celsius.
Yeah, nice, nice. Because the reaction temperature is like in the ATR can go up to 1500, 900, 1500. So 1200 to 1500 or 900 to 1500 or 1200. So the burner temperature, the combustion exact combustion temperature will be very high. Then you can see there will be uh, a thermal gradient. So the temperature will start decreasing as you go down. The correct answer will be B. It is greater than 2000. What is the reaction of enthalpy of this reaction?
Two 47.
247.
And name the reaction.
So
Dry
dry
reforming.
reforming.
Yeah, so it is a dry reforming reaction. You can see the methane is reacting with the carbon dioxide and converting into CO and H2. So answer is A, 247 kilojoule per mole. Which other oxidant is used along with the steam in the ATR process?
It's a B, oxygen or air.
Which other oxygen?
O2, O2 option is B.
Yeah. So you can use O2 or air. Now what is
Air.
the difference if you use O2 or if you use air? Is there any difference?
Yes, in air, nitrogen content might be there. I mean, for where it is, the purity is not required, there we can use air. But where the purity of oxygen is required, then we should use oxygen. I mean, the purity of hydrogen. So
Yeah.
in that case, oxygen to be used.
Nice. So in the fertilizer industry, they are like if they want to produce ammonia, then they can use air, so that there will be nitrogen in the product and also there will be hydrogen, so they can easily form ammonia. If you require pure hydrogen, then you will use pure oxygen. Answer is B. Now, what is the conversion efficiency of sorption enhanced reforming when methane is used as feedstock?
88.
We have one answer, 88%. Think about it and think about the sorption enhanced reforming and let me know.
Sir, 95%.
It is 95% because the purity of hydrogen would be higher because of the sorption enhancement.
Okay, so we have two answers, 88 and 95. Anybody else? Okay. So let's see the answer. The answer is 88%. So first, what are the challenges with conventional reforming? So that we need a different reforming. So the challenge is that the conventional reforming are highly endothermic reactions. Steam reforming, dry reforming. The process is very complicated. Okay. And also if you are having like integration, we want to integrate with like a other process, then we need some intermediate process also. So there will be challenges for the integration. Complete recovery of H2 is not possible. And also the endothermic and exothermic reaction will be there. So difficult to have a single reactor. So we cannot have a single reactor. We need also the water gas shift reaction. So we need to have a different reactor for that. So these are the challenges. Okay. And you can see also the steam methane reforming is methane is reacting with the steam and forming 1 mole of CO and 3 mole of H2. So if you compare, you can see the 2 moles in the input and 4 moles in the output. So you can see the moles are increasing. So when the volume is expanding, so so that reaction will be preferred favorable in the forward direction when there will be lower pressure and higher temperature. Okay, and the delta H is 206 kilojoule per mole. So these are some challenges with conventional reforming. So to overcome these challenges, we need a different kind of reforming. So that is sorption enhanced reforming. So in the sorption enhanced reforming, we can use. So regarding this question, so it is the conversion efficiency. It is not about the purity. So when you ask about the purity, then you can say, okay, the hydrogen can be 95% pure, but the conversion of methane will be around 88%. So you can see if you are having a CO2, so that CO2 can react with with a sorbent and can convert into a, so that sorbent will attach to so the CO2 will attach to the sorbent, and you can see the CO2 gas molecule A is a sorbent, so it will become A dot CO2. So sorbent so the CO2 will attach with the sorbent. So in this way you can remove that and further you can separate out the CO2. So the overall reaction can be like this: the CH4 plus 2H2O plus A is sorbent, so it will become 4H2 plus A CO2. So the conversion of methane is 88%. The purity, so 95 to 98 volume percent of H2 and 3.46 mole of hydrogen per mole of CH4 versus 4 mole of H2 per mole of CH4. So in the steam reforming, you can get 4 mole, but in this you can get 3.46 mole of H2. Now in steam reforming, you can get around 3.46, but here you can get 4 mole of H2 per mole of CH4. Less fuel required and thermoneutral process. So again, I forget, sorry. So what is the most widely used sorbent in sorption enhanced reforming process for hydrogen production? You can see the answer is calcium based. So the most widely used. So you can have different type of sorbent, but the most widely used the calcium based. Okay, and you can see in this diagram. So we are having a reforming catalyst and then calcium oxide is a sorbent. So we are adding the methane, steam, then the temperature 600 to 725 degrees centigrade. Okay. So you can see the reaction will be like this. So this calcium oxide will react with the CO2 and will form calcium CaCO3, calcium carbonate. And this calcium carbonate you can remove it, and in another reactor you can regenerate the calcium oxide. Okay. So for the regeneration you need to maintain high temperature. It will regenerate. So the calcium oxide will be release the CO2, and you can separate out the CO2. You can also can be sequestered in the carbon capture and utilization storage unit. Okay. So and also you can see here. So you can again supply the calcium oxide into the reforming reactor, and in this loop the whole reforming can happen and you can have pure H2. So the beauty of the system is that we don't require water gas shift reactor. Okay. Also you can see the purity of hydrogen can be directly, because the CO2 is directly going there, and if you are only having methane, so you can have pure hydrogen directly. Okay. The H2 content in the SMR reaches a maximum of 76% at 900 degree, and in the SCR, so in SMR steam methane reforming it reaches only 76% at 900 degree. In the sorption enhanced reforming it can go up to 96% at 650 degrees centigrade only. So see the difference. So in the SMR you need to maintain 900 degrees centigrade temperature, then only you can go up to 76%. But in the SCR you can achieve 96% at 650 degrees centigrade, 95% till 750 degree, and above 850 calcium carbonate not formed. So it will not work above 850 degrees centigrade. So because this reaction will not work at above 850 degree centigrade. So this is about the sorption enhanced reforming, and the widely used sorbent is calcium based. Now, what are the benefits of sorption enhanced reforming? So the benefits, as we have already discussed, few processing steps, no need of water gas shift reaction and separation of CO2, low temperature of operation, purification step is simpler, cost reduction in terms of materials, okay, and heat required is low, better methane conversion and better selectivity towards hydrogen product. So we can have more hydrogen, and also the conversion is more. So these are the benefits of sorption enhanced reforming. What is the main requirement of the membrane used in the hydrogen membrane reactor? Low pressure, high temperature, high selectivity of hydrogen, low porosity.
High selectivity of hydrogen.
Because if we are using a membrane separator, then this membrane should have high selectivity of hydrogen, so that the most of the hydrogen can be separated out. The answer is high selectivity of hydrogen. The temperature required during the non-catalytic partial oxidation reaction used for hydrogen production lies in the range of 800 to 900 degrees centigrade, 1200 to 1500 degrees centigrade, 1600 to 1700 to 20 to 50.
1200
to 15.
So we have option like 1200 to 15. Anybody else? Okay. So you all are right. The correct answer is 1200 to 1500, because and where we use this non-catalytic partial oxidation?
When we have different kind of feedstocks, wide variety
Yeah,
of feedstocks.
wide variety. We have heavy oils like residual of refineries processes. So we can use this method. And what about the pressure? What is the pressure
Pressure
range?
is 50 to 60 bar.
50 to 80 bar.
50
Yeah.
to 80,
80 bar. Yeah.
Yeah. What is the temperature range of the catalytic partial oxidation process used for hydrogen production from hydrocarbons?
600 to 900.
So sometime you can also go from the options. So you know the option D, 220 to 50. So it is wrong because at this temperature no reforming will happen. 400 to 500, again it's low. Then 1200 to 1500, it's high. So it's for the non-catalytic. Then only remaining option is 600 to 900 degrees centigrade. So sometime if you have some confusion, try to go by options. So the correct answer will be A. Now what happened in the catalytic parts of oxidation? So the catalyst, because we are using a catalyst, so this will lower down the temperature requirement. So the temperature earlier required was in non-catalytic one was 1200 to 1500. So if you are using a catalyst, so that will lower the activation energy and all. So the temperature requirement will be lower. So the required temperature will be now in the range of 600 to 900 degree centigrade. It increases selectivity of product, mostly reported for methane, but can also have higher hydrocarbons, syngas selectivity, and higher methane conversion above 750 degrees centigrade. These are the reactions involved in the catalytic partial oxidation. First is the partial oxidation, methane plus oxygen, and carbon monoxide and hydrogen, dry reforming, water gas shift reaction, Bordeaux equilibrium reaction, combustion, combustion, combustion. So you see the methane combustion, then the CO, and then the H2. So these reactions can happen in the catalytic partial oxidation. So the equilibrium decided by these equation and hence methane conversion, selectivity and yield. So these three things like the conversion, selectivity and yield will be decided based on these reactions, and this reaction will depend on the operating condition, feedstock, temperature, pressure, and these things. Okay, so these are dependent. So in summary, for catalytic partial oxidation, you can say it's require high temperature, short residence time, heat and mass transfer, and there can be hotspots. Gas composition determined by many factors like feedstock, thermodynamics, and catalyst. It requires small footprint. It can have modular construction, simple operation, fuel flexibility, and flexibility in production capacity, lower capital cost, and energy consumption. Now, what are the challenges? So the challenges are short lifespan of unit due to carbon formation and catalyst sintering. So there can be carbon formation and sintering. So that will damage the catalyst. To achieve high purity undiluted syngas, oxygen is preferable to air as an oxidant which requires additional cost of gas separation. So for having high purity or undiluted means there will be no nitrogen. So you need to have a different unit for air separation. So it will increase the cost. Safety remains a concern as the exothermic nature of reaction generate extreme hotspot with elevated temperatures that ignite a range of methane and oxygen mixture should be operated outside the explosive limit. So because you are having a fuel and oxidant together, so it can also ignite like explosive can be the explosive. So it's the temperature should be below the explosive limit. There is a lack of catalyst oxygen carrier suitable for efficient and stable operation while still being economically viable. What is the key component of ATR?
Burner.
The burner inlet shape tube's outer shell.
Yes, burner.
Okay. Do we have tubes in the ATR?
No, no.
So tubes normally used in the steam methane reforming reactor. Okay. So the main thing is the burner. Dry reforming is a process. Endothermic, exothermic, neutral, and non-catalytic.
It's an endothermic.
Endothermic.
Endotherm.
Okay, the correct answer will be endothermic process. What is the temperature range of dry reforming of methane?
900 to 1200 centigrade.
It will be 900 to 1200 degrees centigrade. What is the H2 to CO ratio in bi-reforming process used for hydrogen production?
2. It's a 2.
We have an answer 2. Anybody else? What is the bi-reforming?
It is the combination of dry reforming and we are adding the steam.
Okay,
Means SRM.
SMR. Okay, so you are having the combination of both. So that is bi-reforming. Okay. Anybody else? So the correct answer is 2. So the bi-reforming. So the bi-reforming have 2 oxidant. The one is steam, and the other is carbon dioxide. So we use both H2 and CO2. So it's a, you can say the kind of a combination of both dry reforming and steam reforming. So the overall reaction can be 3CH4 plus CO2 plus 2H2O can become 4CO plus 8H2. Now if you see the ratio of H2 to CO, so 8 by 4, it will become 2. Okay. So this is so the answer is 2. So in the bi-reforming, there will be some other reactions are also. Water gas shift reaction, dry reforming, reverse water gas shift reaction, then partial oxidation, Bordeaux reaction, methane decomposition. Okay. So these are the side reaction. So for more understanding about these, you should learn the reaction kinetics. The H2 by CO ratio equals to 2 and it can be adjusted. So if you want a different ratio, then you can change it by changing the steam to steam plus CO2 ratio, temperature and pressure. So basically you can change the steam to methane ratio, CO2 to CH4 ratio. So if you change this ratio, then the H2 by CO ratio can be changed. The operating temperature is 700 to 950 degrees centigrade. The pressure is 10 to 30 bar. And now what are the advantages? So we can use the greenhouse gases to produce hydrogen like DRM. And the ratio of H2 to CO appropriate for various downstream production process. So in the downstream you require a particular kind of H2 by CO, so you can maintain that. Less of carbon formation and reduce catalyst deactivation than dry reforming. Why?
Because steam is used in this.
Yeah. So we are using extra steam so we can avoid the carbon formation and reduce the catalyst deactivation. What is the operating temperature for dry reforming of methane used for hydrogen production?
700 to 1000 degrees centigrade.
Okay, so we have an answer 700 to 1000. Anybody? And what is the tri-reforming?
Actually, three oxidizers are used: steam, CO2, and uh, steam, CO2,
Oxygen.
and oxygen. Yeah, three.
Okay, so you will use both steam, oxygen,
CO2, CO2.
and CO2. So the answer will be, we have one option, 700 to 1000. So in the tri-reforming, you can see there are three oxidant, O2, H2, and CO2. So it's a combination of steam methane reforming, tri-reforming, and oxidation. And also the other reaction can be water gas shift reaction, partial oxidation, then the CO dissociation, methane cracking. So these reaction can be there. The operating temperature range is 700 to 1000 degree and pressure is around 20 bar. H2 to CO achieved is 1.2 to 1.5. And the catalyst, nickel, PD, IR, platinum, rhodium, and support aluminum oxide, magnesium oxide. Okay. So these supports can be used. So this is about the tri-reforming. So basically we have covered different types of reforming, and we have seen that in each reforming, mainly we are changing the oxidant. Either we are using only O2, either only H2O, either CO2. We are using combination of two, we are using combination of three. Okay. Then for the CO2, we are using a sorbent to remove the CO2 directly in a single step. So basically our aim of the reforming is to have pure hydrogen or a required syn-gas ratio, H2 by CO ratio. So based on that, we are having different reforming techniques. So those who are working in an industry, they can plan a reforming reactor based on the requirement. So yeah, thank you. So this is my email ID. Anybody who is having any query, you can also email me. Okay. So now it's for from my side, it's okay. So anybody working with reforming in, because I think so many of you from our industries. So anybody is working on reforming or like hydrogen production, or just you want to move into the hydrogen production?
Yes,
Okay.
myself Ravi. Yeah, I'm working in an industry which is producing iron. The process is called as direct reduced iron. So
Sorry, what is the process name?
direct reduced ion.
Okay. Yeah.
Okay, so for this process we require hydrogen because we have to remove the oxygen from the iron ore.
Mm-hmm.
So for that we need reducing gas.
Okay.
So for
So
that the feedstock available is methane, the natural
methane.
gas.
Okay.
Yes.
So
So
currently, how are you using the hydrogen? So are you purchasing the hydrogen or what?
no, we have the reformer.
So you have the reformer.
Our reformer is called as natural gas reformer, but it is a partial combination of steam methane, like by reforming, we can say.
So you are using
Because
basically by reforming.
yeah, but
Okay.
technically we say it as a NG based catalytic reformer. As you mentioned, as we studied in the class, we have a lot
Okay.
of tubes inside the reformer. We have almost 480 tubes. The reformer
480
is
tube. And
yeah,
what is the capacity of your reformer?
reformer capacity in terms of volume you're asking, or
Like how much of hydrogen that can produce per day?
see, the reform gas flow is somewhere near to 3 lakh normal meter cube per hour.
Okay.
Okay,
Yes.
in that almost 60% hydrogen is there. So you say like 1,80,000 meter cube of hydrogen is coming outside the reformer per hour.
Oh, nice.
Yeah.
And
Very big reformer.
what is the feedstock flow rate? The methane flow rate?
Methane flow rate is like 35,000 meter cube per hour.
And you are using the natural gas or you are using like biogas or
No, we are using natural gas, but we are in the transition phase to switch over to renewable energy and produce hydrogen and inject
okay.
in our process.
Mm-hmm.
Because this natural gas, with this process, we are
So
emitting like
yeah, CO2, I
400,
think
yeah,
So
400 kg of CO2 per ton of DRI production.
so how much kg of CO2?
400 kg approx.
400
Yeah, kg of CO2 per ton of DRI. And this is the process which is having
per ton of what? Per ton of what?
per ton of the ion production,
Okay,
producing ion.
Ion,
Okay.
okay. And have you calculated the amount of CO2 per kg of H2?
So we didn't calculate it.
Okay.
And this
Okay.
is the process, the direct reducer process, which is having low CO2 emission, other than the blast furnace or some other process.
Okay. So are you
Like
also
dry.
using water gas shift reactor in your plant?
No, we don't have water gas reactor because
So so you're directly
uh,
using the hydrogen and CO.
yeah, we are using hydrogen and CO in the furnace for reduction, but that
Okay, in the
hydrogen
furnace. Okay.
CO comes from the reformer.
Mhm.
Okay. So in the
So you
feed
don't
gas,
need the pure hydrogen.
we no see that depends upon the process condition. If we want to go for 100% hydrogen, then we cannot use natural gas. We have to
Mhm.
go with some other methodology like electrolysis process, where only high
No, you
H2O.
can, no, you can still get 99% purity from the methane, but you need to increase the steps actually. So you need to install water gas shift reactor, you need to install the PSA, so that will increase your capital cost. But
Right,
you can
right.
have, you can have pure hydrogen with methane also.
Yeah.
So yeah, but it will
In,
increase your capital cost, yeah.
yes, in some other DRI plant, as you said, the PSI is there to remove CO2. But as we said, the capex will increase and also the OPEX, the operational
Yeah,
cost per ton
OPEX
of
will also
DRI
increase.
also increase, and we have to go for a lot of maintenance to change
Hmm.
those catalysts.
Yeah,
And also it is not so much this one what we say feasible for operation.
right.
But right now, a lot of innovation is coming in this field.
Hmm.
So there is another one process called the HOL, where the reformed gas is having like 75% of hydrogen,
Okay.
10%, 15% higher than our process. And they are trying to produce hydrogen through renewable sources and to replace with the methane directly. So
Hmm.
innovation is also going on.
Nice. Yeah, thank you, Ravi, for sharing this so much details about the actual reforming unit.
Yeah.
So yeah, it's very good
No,
to have.
yeah,
Yeah,
in
it's very
future
good to have.
also, sorry to interrupt. In future also, we want to work together in this field to do some thesis or some project
Yeah.
if there is
So you
possibility.
have my email ID. So if you need any information, you can contact me because I'm also working in this sector. So maybe I can help you.
Yeah, sure.
So yeah, thank you, Ravi. So it's very good to have a good
Mr. Ravi,
discussion. So
sir, Mr. Ravi can give his telephone number and as well as his mail ID so that we will get in touch with him and get certain information, sir. Please, sir.
so please don't share your mobile number over this meeting. So
Maybe
you
the
can,
mail ID, mail ID,
yeah,
mail ID.
mail ID you can write in the if you want to share. So like suppose maybe because maybe other students can like want to connect with you
Interact.
to learn more about the actual reformer. So maybe they
Yeah.
can have a meeting with you separately. So you can, if you want to, then you can share your email ID in the chat
Sure.
box in the Q&A. Yeah.
Yeah, actually, in most of the industries, manufacturing industries, the CO2 emission is higher in the iron and steel industry. It is
Yeah.
contributing near to 8 to 9% of CO2 globally. So, lot of iron and steel industries are looking to go green.
Yeah. So
Okay.
no. Actually, every industry is moving towards green hydrogen. Yeah, because in fertilizer also. So in the fertilizer also for the ammonia, so they are using this normal gray hydrogen. So it's not good. So they're also planning to increase the mix of green hydrogen in steel industry, in refineries, everywhere. Yeah.
Yes.
Yeah.
Okay.
Okay. Nice discussion. Thank you, Ravi. Thank you.
Thank you.
Anybody else
Thank you.
want to say something? Any because we still have 4 minutes left. So if anybody have any doubt regarding the slides, PPT, so you will receive the link, and I think one of you have already uh, informed us that you can find the link of the PPT and the videos in the course portal itself. Okay.
Is it Mr. Ravi? Is it willing to share his mail ID, sir?
Yeah, but I am just looking for the chat box. I am not finding the chat box.
So actually you can type in the Q&A. There is a Q&A. So I think in that Q&A you can mention, I think.
Okay. Just a minute. And we have solved some problems, and we have some queries in the problem also.
So if you have any queries in the problem, so you can email me. So maybe in the next class, we can discuss that.
Okay. Please note down my email ID. It is not working. The Q&A, I cannot type anything.
No, my mail ID, I think you can see, no? So my email ID is this.
Okay.
So it is in the end of the slide. So you can also find it online. So it aks.iitd@outlook.com. So those who are having any query, you can email me. So I will try to answer as soon as possible, or otherwise I will discuss in the next class.
Okay. I have shared my mail ID.
Okay. So, uh, yeah, I think your mail ID is here. Yeah. Okay.
Amit, I have a very fundamental question.
Yeah, please.
Sorry, see, is there any quick reference book from which I can get back to the fundamentals of all the mole-related calculations which professor explained in the class? I've been totally out of this touch in this field.
Actually, the basic about the mole. So maybe nowadays you can ask ChatGPT. I think that is also very helpful.
No, I don't.
So
No, I don't want to use ChatGPT. All garbage will be there. I don't want to get into ChatGPT.
so if you want to really like read, then it's better to start with the like basic fundamentals of the chemistry from the 11th or 12th, like the basic
Correct.
fundamentals
Okay.
of moles. So that will be good.
There,
And
I'm totally out of that.
and also
11th or
you can
12th?
11th 12th. Yeah, so there will be basics of moles calculation and all.
Okay.
Yeah, NCRT, you can refer NCRT books.
Okay.
And
11th or 12th.
also you can use the this An academy, I think in an academy they have also provided some content. Some good teachers have also given some content online. So you can also refer that. And also there is a website, I'm remembering the name. It's let me just check. It's Libra, Chem Libra or like that. So let me check the name.
Okay.
So that website is very good actually. Yeah. So you can also refer that website.
Is there any like
Chem Libra.
online?
Chem Libra. I think Chem Libra. You just Google it. You will find the correct name. Yeah.
Is there any online like reference
Okay,
book
right,
available
That's
so that
fun.
fundamentally if
The reference book, I think in the course portal itself, the professor has already mentioned some reference books.
Okay.
Yeah, so you can go through those books, and maybe those books directly, I'm not sure they are available or not, but you have to find.
Yeah, got
Yeah.
it.
Yeah. Okay. Thank you everyone for joining.
Okay.
So I hope you enjoyed the session and you learned something.
Thanks, Abhay.
Yeah. Thank you. Thank you everyone.
Thank you. Thank you all.
Yeah. Bye bye.
Thank you. Thank you all.
Thank you.
Thank you.